All right. I'm going to just get started with introducing the lab. Please start passing your papers to the hallway if you haven't already, to the aisle rather, and Sergey will be picking them up as I speak. Yeah, let's start talking about the lab. So, so first of all, what's the purpose of the lab, right? So what we really wanted to try to do with this lab is to walk you through kind of what a sort of mature, relatively mature machine learning code base looks like, from training to deploying. And so the project that we picked for this was the following, right? So let's say that your goal is to build an application where a user can take a picture of some handwritten text and then press submit, and then what they want to get back is the transcribed text from that they wrote down. And so the first thing I want to do is just talk through kind of an abstract system diagram of how our approach is going to work. So there are three modules that interact with each other. The first is a web backend that takes input from the app and sends input back to the app to output to the user. And then that sends and receives information from a compiled prediction model, which is like your machine learning model that's going to be deployed. And the compiled prediction model is determined by some training code. A little bit more detail, the web backend is going to receive a post request that contains an encoded image. It'll decode that image into something that the machine learning model can understand, and then pass it to the machine learning model. The machine learning model that we've developed actually has two separate components. The first is a line detector, and the goal of the line detector is to pick out each line of text in the image. The output of the line detector is kind of is an image that contains only a single line of text, and that goes to a line text recognizer module. And the job of that module is to take that line of text and then turn it into the actual text itself. And so then the output of that is encoded and sent back to the user. And so how do we actually create this prediction model? Well, one way you can think about this compiled prediction model is it's a set of weights that are learned, and those weights are wrapped by some code that tells the application how to use those weights in order to create predictions. So where do the compiled weights come from? Well, so we'll have some data set and some training code, and those things will get combined into a compiled model in sort of the software 2.0 way of looking at it. We're searching for the best program to solve this problem. And then those will be fed into the compiled prediction model. OK, any questions about the overall architecture of the thing that we're going to walk through? Great. So the first thing that we'll talk about is sort of some of the setup for training. So what does a good machine learning code base look like in terms of how it manages data, how the training code works, and how weights are stored and stuff like that. And then we'll talk in more detail about the architecture and the training code for this line text recognizer module a bit later. And then tomorrow we'll talk about line text detector and the web backend. All right, so the outline of the labs. The labs are kind of compressed into 4 sessions, but there are actually 9 separate labs. So the first thing that I'll do is just walk you through. So this is what I showed you before is the abstract representation of the system that we're going to build. The next thing I'll do is walk you through some of the code that we've created. Then we'll talk about single character prediction. So before turning an entire line of text into text, we'll start with a simpler problem, which is just predicting a single character. And this will allow us to get introduced to the code that we have for training models. And then we'll talk about the full line text recognizer model, which is going to be trained at first on a synthetic data set. And the model that we're going to use is an LSTM with a CTC loss. And I'll explain what that means. And then we're going to talk about some tools for experimentation that we'll be using. So weights and biases for experiment management, and then some scripts that we've written to do parallel training for hyperparameter search, for example. Then we'll give you a little bit of time, hopefully, to try some things out on your own. Maybe let some models train for a while and see if you can make improvements. And then tomorrow we'll train the line detector model, and then we'll talk about managing data, labeling data, versioning data, then talk about testing and continuous integration, and then finally we'll talk about deployment. All right, any questions about what we're going to go over in the labs? Okay. So the first step is to go here to this URL, github.com/fullstackdeeplearning/FSDL Text Recognizer project. So this is going to be where you can follow along with the labs on your own.
Any chance someone can Slack that?
Yes, that's a good idea.
Can one of you do it?
Okay, and when you pull it up, it should look something like this. All right, and so there's some setup instructions here at the bottom. We're going to punt on these for a second, and the first thing that I'm going to do is I'm going to walk you through kind of the overall structure of the code base. So if you go into the folder Lab 1 Solution, then you can follow along with the code base tour. And so ignore this first part here, and essentially what we're going to try to do here is just get you familiar with the overall structure of the code that we have in place. And if you want to, the other thing you could do is change into the Lab 9 solution directory, and then that will allow you to actually poke around all of the files in kind of their final forms as we go through this. Okay, but just so getting started with the structure, the first folder that you'll see if you look in that Lab 9 solution folder is this API folder. And so this is really where the web backend lives. So this is all the code for kind of serving predictions and and providing a nice API for whatever app that we develop to access. In this folder, you'll also see a test. So there's a quick test here just to make sure that our predictions are working, so that we don't deploy something that is broken. And then there's a Docker file. And we're using Docker here. If you don't know what Docker is yet, don't worry too much. We'll talk a little bit about it. But Docker is essentially a way of provisioning virtual machines. And so we use this as a way of making sure that the code that we're running in production actually has all the requirements that we need, given how we train things. Then there's app.py, which is actually the logic for the Flask web server that serves the predictions. And then finally, there's this YAML file called serverless. And this is specifying an AWS Lambda deployment of this application. And Sergey will talk more about that tomorrow. OK, up one level in the hierarchy in the Lab 9 solution folder is, actually just under the main directory structure of the entire project is the data folder. And so this is not under version control because often your data sets are large and you don't want to be constantly pushing changes to large data sets just to GitHub because then every time you pull it's going to take a long time. And under that data folder there's another folder called raw, and then that raw folder contains these 2ML files. And what these are essentially specifications that tell our code how to actually download the data when it's time to do so. And so again, the raw data is not stored in this directory, but we're storing the instructions for how to download it when the time comes. Any questions up to this point? OK. So the next category of things is tools for experimentation. And so there's a folder called evaluation. And under evaluation, there are some scripts. And those scripts allow you to quickly evaluate your model on some evaluation set. And the utility of this is as you're developing, you train some new model, and you might want to just be able to quickly test how well that model performs. And so and oftentimes also the way that you'll use a script like this is as a unit test that maybe depending on how long it takes, maybe you have to pass this unit test before you merge any changes to master branch in GitHub, or maybe it runs overnight. And then there's a folder of IPython notebooks. So IPython notebooks are a great way of just doing some initial exploration into some new idea you want to try, some data set that you want to learn more about. So typically the workflow will be you try something out in an IPython notebook. When it starts to work well, then you'll move it into, turn it into regular Python code so that it can be used by the rest of the application. Then there are some convenience scripts for things like deployment, checking code quality, running tests, and training. And then the meat of this is really the model and training code. And so there are two folders here. The first is Text Recognizer, and then the other is training. And so we're splitting up actually all of our training code except for the training loop itself. We're creating that separately from the code that creates the models and the data sets, et cetera. And the reason for that is because we want to essentially zip up this Text Recognizer folder and then send that into use that as a self-contained prediction system when we deploy the model. And so we're just isolating any parts of the training code that don't need to be used in deployment from that system. So within Text Recognizer, there's a couple of predictor files. And the goal of these files is really this is actually what you're going to be using. This is actually the function that's going to be deployed. And so what these do are they wrap the model classes essentially. And they tell you how to take a raw image and then convert that into a prediction. So it's just a really simple function, takes raw image in, outputs prediction, and it uses the rest of the code. Then you have some data sets code, and the distinction here is that we had a data folder, and that contains the raw data, and then the data sets are everything around the raw data that you need in order to interpret the raw data in your model. And so I think this distinction is super important in machine learning code bases because you can, a lot of times you'll collect new raw data or you'll evaluate on a different data set or something like that, but you want kind of the logic about how to stream data to your model, how to pre-process data, how to augment data. You want that to be separate, and so that logic lives in this datasets folder. And this also tells the system how to download the data according to the specifications in the data folder. The next category here is models. And so this is, so there's models and networks. And the distinction here is somewhat subtle, but I think is actually super important for making healthy machine learning code bases. So, and it's pretty similar to the distinction made in Keras, for those of you that are familiar with it. But the idea here is a network is a dumb function that takes some input that it doesn't understand and produces some output that it doesn't have any context for. So it's just a neural network, basically. And then the models class contains everything else that's important for that network to do its job. So it tells the network how to translate the raw outputs into predictions that are interpretable by us. It tells the network how to take raw data and turn it into the data that is in the right format for the network. That's where you have loss functions, for example. That's where you have you might contain your optimization code in the model as opposed to the network. So this is kind of everything around the neural network that's important for making the neural network work. Then there's some tests, and Sergey will talk more about these. And then lastly, in this folder, we have a weights subfolder. And so what we're doing here is we're actually saving the weights for the production model, for each of the production models that we use in this same folder. So it's just easy to kind of serve them up. And we always have a canonical, this is the model that we're using in production, and the weights for it are saved there. In practice, you'll have trained many, many, many other models, and the weights of those will all also be saved somewhere, but you wouldn't save them in this folder. Those would be saved maybe on S3 or something like that, and you'd have some way of accessing them. OK, and then lastly is the training code. So this is code for running training experiments and selecting the best model. And the important files here are this util.py, which is actually the logic for, given a certain config, how do you train a model according to the specifications that that config gives you. And then run experiment, which is how you parse configs and launch training. And we'll talk in more detail about most of these files throughout the course of the labs. Any questions up to this point? Yeah?
So all of your setup is pure Python. Could you maybe touch a little bit on like multilingual stuff?
Yeah, so the setup is pure Python. I've seen like most machine learning code bases are mostly in Python. And like oftentimes there's, maybe you have like some like, so this happens for us for rendering code, for example, which is like, we need it to run super fast, so we run it in C++. And typically like we would just have another folder under the main directory structure called like source or vendor or something like that, where we would throw like any C++ packages in there. Yeah. Yeah.
Could you touch upon like any labeling tools? Is it just open it in VI and label it, or?
Yeah, we will touch on a labeling tool, and I think Sergey will talk about like some alternatives. But we have one that we're gonna have you all label some data so you can understand the pain that goes into data labeling. Yeah.
At some point, if you could comment on how to deploy models in a Java ecosystem.
How to deploy models in a Java ecosystem. Yeah, not an expert on that. We won't talk about that. Yes, question here.
In case you want to extend your data set and you were expecting to have more data, for example, you add a new, like, I don't know, metadata on something that was taking the picture of the text. How do you work with that? So is it in a data set folder? Like, so you add the pre-processing, but how do you change your model?
Mm-hmm. So is the question like, how do you, like, let's say that you add more information, like more like different types of labels?
Okay, what is the workflow if you're expecting to add more data sets that are kind of like more features?
I see. What is the workflow if you're trying to add more data sets with more features? I think Sergey will talk about this tomorrow. Yep. Yes?
How is it different from Tesseract?
Not familiar with Tesseract. Yeah.
The OCR system. I mean, Tesseract is not neural network based.
Anything else about like kind of how the code is organized and why we split things the way that we split them, where certain parts of the code should live? Yeah.
Just want to clarify, we are going to use AWS Lambda functions, right?
Yes.
AWS infrastructure in general.
In AWS.
Like, in general, we're going to focus on AWS.
So the question is, in general, are we going to focus on AWS? We have or will have at some point today. There's been some technical issues. GPUs available for you all to use, and those will be on Google Cloud. And then, but we're going to do deployment with AWS Lambda. Yeah. Maybe I'll take these two questions and then I'm going to move on. Yeah.
So this is the structure of the repo you recommend for production quality code of machine learning of the repo, but when you're still in the experiment phase, you also recommend us to follow the structure and also separate all of our different sub-modules of the app.
Yeah, so this is a great question. So the question is, this is like what it should look like at production stage, but what does it look like before you get to production stage? When do you move to a structure like this? So the way I typically think about it is like the first version of code I write for a new project, like I want it to be a single line of a single file with as few lines of code as possible. Like rule of thumb that I use is like 200 lines of code. And I mean, like stuff that like tested infrastructure stuff doesn't count. Like you're allowed to use. You don't have to write TensorFlow from scratch, for example. But and then I'll move from there gradually as the project develops to a structure like this. And so the first thing I'll do is like maybe let's say I'm experimenting with like lots of different loss functions for the same model or for the same network rather. then maybe at that stage I'll be like, okay, now maybe it makes sense to pull out networks into its own file because I'm changing things that happen around the network a lot, but I'm not changing the network that much. So I'd rather just not deal with the complexity of looking at that code every single time I want to change the loss function. That's a great question. OK, I'm going to move on from this. So this is the end of lab 1. So we're moving on to lab 2. So Sergey, are we set up to use?
I think so.
OK. All right, so the next thing that we're going to do is we're going to kind of walk you through setting up the cloud environment that we're going to be using throughout the labs. And so the first step is to go to this URL, so app.wannadb.ai, and sign up. And you can sign up with your, get your GitHub username or your email or whatever you want to use. So while you do that, just a little bit of context. W&B, or I call it WannDB sometimes, or Weights and Biases, is the full name, is a machine learning experimentation management tool. And we'll talk more about this, but essentially the thing it's really useful for is keeping track of all your experiments in one place and being able to refer back to experiments that you ran a month ago and know that you're still going to be able to access them and compare to them. OK, how are we doing on weights and biases setup? Raise your hand if you need more time to do this. It's slow? OK. Yeah, oh yeah, so Cal Visitor might also be the reason that it's slow. It's very possible. Cal, for one of the foremost universities for technology, we really don't have very good Wi-Fi. It's very sad. OK, why don't we do this? The instructions are here for how to get set up. I'm just gonna start moving on, and it's not like super critical that you can do this all live with me. So like basically, kind of the principle for how we've structured these labs are we have like kind of all the code available in the solutions folders, and since we have limited time in the labs, I'm basically going to be spending most of the time walking you through the code that we've already written. But then we've also provided the lab folders that don't have solutions. And in there, they're kind of like exercises for, fill in this part of the code in order to make this thing work. And those are meant to be done on your own time. And so ideally, we can have you all follow along with what I'm doing live. But since it seems to be taking so long for everyone to get set up, let's just move forward. And hopefully, you guys can get set up as we go. Yeah. Yeah, the Jupyter Lab instance code is.
I just put in a slot with FSDL hyphen deep hyphen Cajon, C-A-J-O-N, type of musical instrument.
All right. So I've had the luxury of already setting up my my Jupyter Lab before the class began. And so I'm just going to start walking through this a little bit. And the first thing I want to talk about is, like, what is Jupyter Lab? So Jupyter Lab is basically like a web-based IDE. And this allows us, the reason that we're using this is it allows us to all kind of have access to the same requirements, and everyone has a GPU. And then the types of things that you can do in here are, you can browse through the folders. So like I can go into the project folder and I can look at any of the labs. Lab 2 is the one that we're going to do shortly. But then I can also create a terminal like this one, which doesn't appear to be working. And so I can just interact with this machine through a terminal, or I can create a Jupyter notebook if I want to just run some code on this machine and just see what the output is. It's having a lot of time with this one, 2 plus 2. So maybe there's something going on with the GPU or something like that. But the thing I really want to do is I want to start by talking about kind of walking you through what our training code looks like. And so the place to look for this is in the Lab 2 solution folder. Okay, and so this is going to give us kind of the outline of what we're going to talk about today. And then you can go into the subdirectories here and follow along by reading the code. So really the goal of this Lab 2 is to, we want to end by, if our goal is to be able to read an entire line of text and produce text as output, often a thing that's a really good idea in machine learning is to, when you have a hard problem like that, is to start with a simpler version of the problem. And so the simpler version of the problem that we're going to do is predicting a single character on a data set called emnist. And so the first thing I want to do is just tell you a little bit about emnist and show you what that data looks like. So I'm going to go into the notebooks subfolder, and then I'm going to open up this notebook called 01 look at emnist. So emnist, just to give you a little bit of context, emnist, as most of you probably know, is kind of like one of the most common computer vision baseline data sets. It's a data set of digits from 0 to 9, and like kind of handwritten examples of that are binarized and 28 by 28. emnist stands for mini NIST. NIST was like an early handwriting data set, and they compressed it to make emnist. And emnist is extended emnist, so extended mini NIST. So like, seems like a little bit weird to me, but it's maybe you can think of it as being part of the way between emnist and NIST. And so if we have this class called emnist dataset, and we're mostly going to treat this as a black box for right now. But if we create this dataset and then we print it, then we see that emnist has 10 classes. emnist has 80 classes. And so instead of just the digits, it's the digits and all the capital letters and the lower letters and some special characters as well. So this is kind of like the base data set that we're going to be working with for handwriting recognition. So if we call loader generate data on this dataset class, this is the function that actually goes and downloads the data and makes sure that we have it locally. Then we can look at kind of the shape of the data set. And so there's about 700,000 images in the training data set, and they're all 28 by 28. And then the labels are 80 dimensional because they're 80 characters. And I think like the main thing that you need to know about these data set classes is that you can access these attributes, xtrain, ytrain, xtest, and ytest, once you've called loader generate data. And then that's the data that's going to be fed into your model for training. So what do these things look like? Here are some examples. Essentially they look like emnist digits, but with more variety. Okay, so that's emnist. And again, our goal is to train a model on emnist. So let's look at the code that we have written for actually creating and training models. So the first thing that I'm going to do is I'm going to go into the Text Recognizer/network/MLP class. And we're going to look at kind of the most basic network code that we have. And so essentially what this does is it's not a class, it's a function. And it takes as an input, what's the shape of the data that we're inputting and what's the shape of the output that we want to create. And then some parameters about how big of layers we want to create and how many layers we want to create. And also maybe some other parameters like how much dropout we want to add. And what it does is it creates a Keras model. So it's just a sequential model. And what we do is we flatten the input. So we're taking like our 28 by 28 images, and we're flattening those out so that they're 28 times 28 dimensional. And then we're passing them through some number of dense layers with some layer size that we've specified, maybe adding some dropout. And then finally, when we get to the end, we're adding one more layer that just takes a softmax over the number of classes that we have. So that's the output that we'll use to perform classification. I saw a question here. Do you still have a question?
Sorry, just a request.
Yeah.
Would it be possible to turn off the light that's
I see. Yeah, so can we turn off the lights? Oh, brilliant. Is that better? Okay, great. Any questions about, like, this is sort of like the simplest neural network that we could create? Yeah.
So is that the return type, like in Python, is it a new Python thing?
Yeah, so typing is a Python 3 thing. Typing, I think, is like super useful to use, like in machine learning code bases in particular, because it's really common to have things that, like TensorFlow, for example, does a lot of automatic casting. And that can produce really nasty results if you're not careful. So yeah, I would highly recommend upgrading to Python 3 and using type checking. Any other questions? Yeah. Yeah, so the ellipses on the top, this is kind of just like some Python, some Python syntax that I don't really want to get into right now. Okay, so that's kind of the simplest possible model. We can do like slightly better than that, which is, our data is images, so let's feed it into a model that's meant for images. And so this is some code for creating a really basic convolutional neural network. So this is Linnet, which is like kind of the simplest convnet that most people try first when they're working on new image data. And so, essentially this works exactly the same way, but instead of adding dense layers, we're instead first adding some conv layers. And then we are pooling to reduce the size of the representation. And then we're flattening and passing it to a dense layer and then a softmax. So again, Linnet, very simple convolutional neural network architecture, but it's another choice of network that we can use in our setup. Yes?
About the Rockwell rate, 0.2, there's one technique you can increase the Rockwell rate layer by layer.
So the question is, should you increase dropout rate layer by layer? My answer to that is maybe. Like, deep learning is an experimental science first and foremost, and so like at the end of the day, the thing that you should use is the thing that you try and works best. And so like oftentimes you'll see some paper that says like, we have created these activations that work better than ReLUs. They're called, crazy lus or something, and we claim that they work 10% better on every deep learning task. And like generally, I'm very skeptical of things like that because people, like researchers, often choose experiments that make their techniques work well. And so I think like if I saw a result like that, I would say this is worth a try, and maybe it'll work in my setting, and maybe it won't. Yes.
Just a technical question: why Linnet file seems to be empty? Am I expected to fill it right now?
No. So if you see these comments that say, the question is, why is line 12 empty? That's just a formatting thing. But if you see these kind of like these comments that say your code below, your code above, right now we're walking through the solutions. And the goal, like the hope is that if you have time on your own, you should walk through the non-solutions and try to fill out the pieces of code where in the non-solutions they'll be blank. So that's kind of an exercise that we're leaving for you. But because of limited time, we're going to walk through the completed version. All right, so that's the network code. The next thing I want to look at is the model code. So again, the network is kind of a dumb function, and the model is everything that wraps that function. So there's two files here. There's base, and so this is kind of like the abstract class that defines a lot of the behavior of models in general. And then there's character model, which is the specific model that we're going to use for character prediction. If we look at base, the model class takes a few things as input. It takes a data set and some data set args. And really the reason for taking data set and data set args is so that the model knows what its input is going to look like. Then it takes a network function, so the model is kind of managing the network, and then it takes maybe some additional arguments for the network. So maybe you want the user to be able to specify how many layers there are, or something like that. And then what it does is it constructs a dataset class, but it doesn't actually download the data. It just uses that dataset, self.data, as a way of providing the input shape and the output shape to the network. Then there's a couple of other things that are important here. There's this thing called a batch augment function and a batch format function. And these are going to be ways that in subclasses of this model, we can determine the behavior of augmentation and formatting. So we can change kind of what the structure of the data looks like, or we can do some data augmentation. And then I think maybe actually a couple more things I'll say about this. The model is actually, in this case, like the way we set this up is it has this function called fit. And this function called fit is what's going to be called by the training code in order to do your training. And so what fit does is it takes some data set. This is the data set that you want to train on. And then maybe some parameters about your training, like the batch size. And then for those of you who are familiar with Keras, it compiles the network with a loss function, an optimizer, and some metrics. And this is basically just saying, this is the loss I want to compute, and here is the optimizer I'm going to use to take gradients on that loss. And then it turns our data sets into train sequence and test sequence. And so what train sequence and test sequence do is, this is just kind of a way, like we've created this class that wraps some behavior in Keras that lets us kind of stream data to our model without necessarily loading it all into memory. And so it's usually pretty important in code bases where you're working with large data sets to have some provision for making sure that you don't need all of your data loaded into memory at the same time. Yeah.
So as you mentioned, Keras already has a fit. Was this did you write it here to override it for new functionality, or is it just to make it explicit for people not familiar?
Yeah, so we're actually calling Keras's fit method within this. So on our network, we're calling fit generator, right? And so the reason that we're wrapping this in a separate function is because we want the user to have an interface where essentially they just they pass in a data set and maybe some parameters, and they don't need to know anything about Keras syntax. And then all the Keras stuff just kind of happens within this abstract interface. Yes?
Can you explain a little bit about the property decorator function?
Sorry, which function?
The decorator function, property?
Yeah, so property is just a Python decorator. And all it does is, instead of, normally like the way that you'd get weights file name if you didn't have property decorator is you'd call weights file name with parentheses. And then what property does is it makes it so you can just say like class.weights file name with no parentheses. So it treats it as like a property of that class instead of a function. Okay, so that's kind of what the base model looks like. And the next thing I want to do is I want to look at the character model, so the model that we're going to train on single characters, and see what changes we need to make here. And so really the only thing that needed to change here is overriding this method called predictOnImage. And so essentially the character model works exactly the same as the base model, but we have provided some logic for how it's supposed to deal with a raw input image, which is just casting it from an unsigned integer to a float so that it can be accepted by the model, and then passing it to the model, and then the model produces a distribution over outputs, and we just need to take the most likely output according to that distribution. And so this is like kind of the human interpretable output of the model. Yes?
It looks like you're in the character model, you're importing all other network of the base model and everything. So is it like you have to use this final model that is part of character model? I mean, in the imports of this file, you say import the models.base.
Mm-hmm.
So you're trying to import all the network you have created in the previous file.
Yeah, so the imports of this file are just making sure that we can extend the base class. So you don't actually need to import all of the networks in this file. Like the networks will be passed by the training code. So the network function, the function that creates the network, is being passed directly into this model class. Okay, great. So now what we've done is we've kind of understood a little bit about what these models and networks look like. And the next thing that we can try is we can try to actually run training with one of our networks on this EMNIS data set. And so the function to run training looks like this. We have to prepend everything with pipenv run. And the reason for that will be clear if you've made it through some of the setup instructions. If not, what pipenv is it's a sort of it's like a way of managing a Python virtual environment, so that you can manage all of your dependencies. So like everyone working on the same project has access to the same dependencies, and you can be conscious about updating versions and things like that. So the reason why this is so important is that, I'll just give you an example from yesterday. We were making sure that this training code was working, and we had updated to TensorFlow 1.12. And it turns out that when you updated from 1.11 to 1.12, it broke some of the functionality of our training code. And having version management in place allowed us to just kind of really easily downgrade everything and make sure that anyone who uses this code in the future will be using the same version of TensorFlow. Yes?
If we're running a project on, like, say, a container, would you still recommend that we do pipenv? Or have some kind of virtual environment even inside an image for a container?
Yeah, so I think, so the question is, inside of a container, do you still need to have like pipenv or some sort of virtual environment? The answer is, I don't think you really need to. Like if you're using Docker or something like that, then you can just, I think the thing that's important is making sure that you specify the right requirements to Docker. So like one problem that I've seen a lot is, you have some environment that you're using to prototype things on your laptop, and then maybe you use Docker for deployment or for training, and then the versions that you're using locally are out of sync with what's on your Docker container. And so one thing that's kind of nice about pipenv is that everything that you install with pipenv install locally is saved into a text file, and then you can use that text file to specify to your Docker file exactly which versions of each piece of software you need. And then when you create your virtual machine using Docker, you'll be guaranteed that that Docker image has exactly the same versions of all of your dependencies that you're using locally. Yes?
So you just mentioned that it's necessary, or I think you implied that it's necessary to use the same version, for example, of TensorFlow for deploying, same as the one you use for training it. So is it necessary, or is there a way to get around that?
Yeah, so the question is it necessary to use the same version of TensorFlow for deploying as it is for training? I don't think it's necessary, but it's extremely useful. And the TensorFlow, for better and for worse, is still rapidly evolving software. And for better, because there are a lot of things about TensorFlow that are really bad, and oftentimes those things just get better, and that's great. But for worse, because there are a lot of breaking changes in TensorFlow, and so I think if you want to be safe, then you should make sure that you have the same version of TensorFlow everywhere for all of your developers, and certainly in production. And I think there are reasons why you might not want to use the same version of TensorFlow in production, and there are many valid reasons why you might not even want to use TensorFlow at all. But then I think you need to be very, very careful about making sure that that software changes don't break your deployed model. Yes. It's somewhat similar to Anaconda, but better. Yeah. I don't like Anaconda personally. Yeah. What's the question? Sorry.
So Pippy run would pick up the environment from somewhere, like the name of the virtual environment.
Yeah. So the way pipenv works is it maintains two files. One's called pipfile, and pipfile is like a text file that's an abstract representation of your requirements, so that you could manually edit if you wanted to, but it's updated automatically every time you call pipenv install. And then there's pipfile.lock, which contains the exact versions of all the things that you have running in your environment. And those two files together define your environment. Okay, I don't want to talk about pipenv anymore, although it's very important to use a tool like that. But what I do want to do is I want to see if hopefully our virtual machine has kind of worked out some of the issues and we can run training. Oh, I'm not in the right folder here. That's also important. So I'm going to change into our project folder. And then I'm going to change into the lab 2 folder. And then what I'm going to do is I'm going to rerun this command. And so this command is pretty simple. So I'm just running a training script, and that training script is, again, calling the fit method from the model. And it's taking this config, which is this, this kind of like nested dictionary, or you could think of this as like a JSON file if you want to. And this config specifies what data set we want to use for training. So in this case, it's emnist data set. And again, the data set is the thing that wraps the raw data. And then which model. So we're using the character model because we're doing character prediction. And then which network we want the model to use. And so the really nice thing about this is, for example, if you're running multiple experiments, you may have the same model, but you might want to use tons of different network architectures. And so you can just change the network architecture and not have to deal with the model being different. And then we can also pass some arguments like maybe the batch size. Or you could also envision passing the learning rate or something like this into here. And the magic question is, we'll see what happens. Oh, all right. I was about to say we might be having some technical difficulties with our virtual machines, but oh, here we go. OK, and so this kind of runs training as we would expect to. We can also change some things about this, right? So we can, so for example, we can pass in a different network. Like maybe instead of MLP, we want the convolutional network that we described, which is Linnet. Or, for example, we could change the batch size. But this is kind of an example of how the interface that we designed for running training works.
So did you code the models, or did you get them from somewhere?
So we created essentially the models. So the networks are like very, very simple neural networks that are just kind of like baseline architectures. And then we created them using Keras. So Keras defines all the layers and things like that. And then the models, the wrappers for the networks are things that we created ourselves, but they're mostly just using off-the-shelf Keras stuff. OK, great. So basically what we've seen how to do with this code base is we've kind of looked at the network and model code and seen kind of the simple way that those are created. And then we've shown you how to train a model that using different networks and different model specifications and different parameters. So maybe the next thing to try is let's take a pre-trained model and let's try to run a test and see how well that works. And so we have this test called test character predictor. And if we look at this, so if we look at this test, effectively what this is doing is it's just a unit test. And all it does is it imports this from this character predictor file, which remember we said is kind of like the self-enclosed way of creating a model and using it to run predictions. And it creates that, and then it loads some specific images of particular cases that we want to test. And then it runs our predictor on those, and it just tells us whether those predictions are right and they're confident enough. And so this is a very simple example of the type of test that you might want to run for models like this. So let's try it. So I'm going to start with pipenv run because we want to make sure that we're using our pipenv environment. And then I'm going to run pytest, which is just a kind of a way of parsing these test cases. And then text recognizer /tests/test character predictor. So one other important thing to note is that this is using a pre-trained model whose weights that we've saved in the directory because we don't have time to train everything live. So okay, so great. So what this is telling us is that our test passed. We predicted our key examples with the accuracy that we wanted to predict them with, and we have some warnings because it looks like, what is this? It looks like TensorFlow is using some deprecated Python syntax. So we as the users get to bear the brunt of the warnings that are created from that. Okay, great. So that's kind of that's an overview of sort of what the test, the character predictor code looks like. How to train things. What some simple tests might look like. Are there any questions up to this point? Yeah.
I'd like to know how you store the different configs of the experiment and the results that you got from a particular experiment. What do you use?
Yeah. So so the question is, how do you store the configs and the results? The answer is the thing I use and the thing that we'll use in this course is this tool called weights and biases, and we'll talk more about that this afternoon. Yes.
So whenever this is open, is it continuously charging us like Google Cloud? Or is it only when it's training that we have been?
Yeah, I think it's probably charging us as long as this is open, right? Because we're reserving a GPU that no one else can use. Okay. So I think with the remaining time, the thing that I want to do is, so we've started with this very simplified version of our whole problem, right? Like we want to read entire pages of text, and we've started by training a model that can read characters of text. And so the next thing I want to do is talk about what a model architecture might look like for reading entire lines of text as opposed to characters. All right, so again, the goal is we have some inputs that look like some handwritten text, and the goal is to predict what characters correspond to that handwritten text. So what might a model architecture for this look like? Actually, anyone have any ideas? Like, what kind of model architecture would you use for a problem like this? Let's see. So I can't hear all of the things coming at me at once. Anyone want to raise their hand and suggest something?
Some recurrent architectures that process sequential input, like RNN and SQL.
Yeah. So recurrent architectures. That's a great idea, right? We have text that has some sequential structure, and so like a recurrent neural network is sort of the first thing that we should think of. Any other ideas? Yeah. Yep, we need a CTC, and we'll talk about CTC. Question or suggestion? Yeah.
Visual attention here.
Visual attention. I like that suggestion. I think that could work really well, and maybe even better than the thing that we're using here. Okay, I mean, I think the core challenge here, right, is like this is sequential data, but it's also image data, right? And so if we use a model that's purely sequential, that purely moves from left to right, then we're not going to be capturing some of the structure in this data because there's also a spatial structure to it. And so, kind of one baseline that you might use is like, let's simplify this to a character prediction model. And so if our goal was just to take this part of the image and use it to predict the first character, then a model architecture we might use is we might pass that part of the image through a convnet, take the outputs, softmax them, and pick the most likely one according to the softmax and use that as our character, right? So like, how can we extend this to predicting a line of text? Well, we can just we can just take this input window for this convnet and slide it across the entire image. So we can take an identical convnet and apply it to this part of the image, and this part of the image, and so on. And if we do that, then for at each position where we move that convnet, it'll produce one output, and then the result will be like a string of outputs. But there's a couple problems with this. One problem is, like, let's say that we have the model. Let's say we're looking at this window, and there's actually like 3 characters in this window right now. There's a kind of the end of the T, all of the H, and most of the E, right? So the question is like, which of these characters is the correct prediction for this window? And I think the answer is that it depends on the context, right? So we know that at the previous time step, we predicted T, so we don't want to predict T. And so like maybe the next thing to do is to predict H. And so one way that we can capture this time dependency is to add some recurrence to this model. So instead of just taking the outputs and feeding those directly to the character prediction, instead we can add an LSTM on top of those outputs. And so this LSTM, at the first time step, works very similarly to the model we had before. But at the second time step, it takes the output of the LSTM at the previous time step and uses that as one of its inputs. And so this is like one way of capturing the time dependence, the context of this data. Questions about this? Yeah.
Different people have different width of letters, right? When they write letters.
Yeah. This is a great observation. So the observation was different people have different width of letters, and this is kind of a nice segue into the next component that we're going to add to the architecture. Any other questions up to this point? Okay. Yeah. So the challenge, as you pointed out, is like there's different line spacing, right? So maybe this window size makes sense for this line of text, but what if someone writes like this, right? Like same writing, but much more compressed. Then all of a sudden, our window now captures an entire word, and so it's like it doesn't seem likely that we're going to be able to model this accurately with this more compressed text. So like maybe a naive solution is maybe we just make the window smaller, right? So like let's make the window super small, and let's slide that window. But then the question is, what happens when we move back to this more spaced out text? And the challenge here is that with a window like this, you might get the same character twice. So if you slide this window only a little bit, then it's focusing on the T both times. And so what this model might do is it might predict T twice before moving on to any other character. But there's a solution to this. And the intuition for the solution is, like, let's say that we have some input, and we use that input to create some output. But since the window is small, we're duplicating some of our outputs. Well, kind of a naive thing that we could do is we could just compress all of the duplicated outputs into single characters. And then if we do that, then maybe that'll produce the right thing. But the challenge there is that there are some words where it actually makes sense to have the same character twice in a row. And so this won't exactly work, but it's the right intuition. But the answer is this loss function called the CTC loss. And at a high level, the way that this works is you produce your kind of unaligned output that has duplicated characters like before, but we added a special character, which is this epsilon character, like a blank character. And so the model at every time step has the option of predicting a real character or this blank character. And then our rule for turning this into human interpretable word is for all of the adjacent letters that are the same, we compress them into one letter. And same thing for the epsilons. And then we get rid of these epsilons. And so we can now have double letters because there's this epsilon between the first and the second L that doesn't get compressed when we turn this into one sentence. Yes?
So with these duplicate detection, right? So you are building a layer that can detect one character, right? But is it as good for detecting part of a character? Like how can you differentiate between an I and part of a T?
Yeah. So the question is, we know that one thing that works well is if we have a model that predicts like a full character. Like if it just has an image of an I, then it's good at predicting an I. But the question is, what happens if our window slides and it gets half of an I and half of a T? And the answer is, this is part of the training process. So in our training set, we'll see many, many examples of partial letters. And just like if you show me 2/3 of an A, I can probably figure out it's an A. The model will sometimes be able to figure out what the right letter is. But then one nice thing that the CTC loss lets us do is the model has a way of saying, I don't know. And so if it's like really in between two letters and it can't tell which one it should predict, then it can predict this blank character and just like kind of give up on predicting that image. Yes?
So I'm not sure that I get it. How do we force the neural network to predict that epsilon problem? Do we have it in a training set?
Yeah, so the question is, how do we force the neural net to predict this epsilon? And the answer is so two parts to the answer. The first part is we just add this epsilon as like an option for the neural net to predict. And then the second part comes down to essentially I've told you how to compute the outputs of the neural network, but I haven't told you how to train the neural network yet. And I'll talk about that in a second. Yes?
What's the CTC loss, or if you don't know that?
Yeah, so the CTC loss is basically, I'll go over how to compute the CTC loss. Like this is kind of like the abstract way of computing outputs in this type of scheme. Yeah.
So is the point that a trained neural network will help identify the positions where the epsilons need to be inserted?
Yes, the point is that a trained neural network will be able to will have the option to say that it doesn't know what character goes in this position, and then it can use that option as a way of creating duplicate characters if it wants to. Okay, so I've told you like kind of if you have a setup like that, how do you compute, like how do you turn the the string with many duplicates into a string that's like human interpretable. But what I haven't told you is how to train this thing. And I'm going to just kind of go over this at a high level, and there's a lot of technical details for how people make this work in practice. But essentially the way it works is at each time step, you compute a distribution over outputs, right? So you take a softmax, and the softmax assigns different probabilities to each letter in your corpus, including this blank character. And so that gives you a distribution of outputs at each time step. But then what you need to do is you need to use that distribution of outputs at each time step in order to create a distribution over all possible output sequences. So like if your target sentence is hello, then what you need to do is you need to use the per character probabilities in order to compute the probability of the entire sentence. And so you basically have to traverse many paths because there are many different ways that this sentence could create, that this method could create the sentence hello. And so this is, if you do it naively, very computationally expensive. But it turns out that there's like a dynamic programming algorithm that lets you do this in a computationally efficient way. And I'm not going to talk about the details of that. But if you do want to look at the details, there's a good kind of review article that I recommend checking out. Yeah?
So you said you learn a probability distribution over every possible combination of sequences, letter sequences?
Yeah, so the question is the way it works that you learn a probability distribution over all possible sequences. So effectively, like the way you can think about it is at each time step, you have a softmax over characters. And so at every time step, you can say, it's pretty easy to just query that softmax and say, what's the probability that the next character in the sequence is H or E or L? But then what you need to do in order to train the model is you need to look at your target sequence, like say the target sequence is hello. And then you need to look at all of the possible ways of creating hello from this longer sequence with duplicates. And then combine the probabilities of those in a way that gives you the probability of the sentence occurring. Right, because the neural network produces a fixed number of outputs, but then those outputs can be compressed, can be combined in different ways in order to produce the final sentence. Yeah, question in the back.
So in the earlier slide where you stacked the CNN and the LSTM,
Mm-hmm.
you said possible ways that you can add another LSTM to remember what sequence you saw earlier, trying to go over that hello with overlapping characters.
Yeah, so the question is, could you add another LSTM that remembers what sequence you saw earlier? Yeah, I think so the LSTM is able to compress all of the context of the things that you've seen earlier. You can have multiple LSTM layers that'll do a better job of that. Yeah, I mean, actually kind of like analogous to the universal function approximation theorem, which says that for any function, there's a neural network with a single hidden layer of arbitrary, like if you make the size of that arbitrarily large, you can get arbitrarily close to approximating that function. There's this analogous result for recurrent neural networks that says that that recurrent neural networks are Turing complete. So like for any program, you can find a recurrent neural network, I believe, with a single hidden layer, as long as you make it wide enough that can approximate that program.
I was talking about previous to the CNN. So you had the CNN with the spatial thing in the front of the LSTM. So
Yeah, so the question is, could you have a LSTM before the CNN? I don't think there are very many circumstances where it would make sense to do that, but maybe, yeah, I'm happy to talk more about it offline. Okay, so that's kind of like, that's an introduction to the model that we're going to train to do line detection. And so the next thing that we will do is talk about the code for creating this model. And let me actually just quickly start on that.
Can you go over the CTC loss function again?
Let's talk about it offline. Yeah. So the first thing that I'm going to do is, and so if you want to follow along here, then go into Lab 3 solutions. And then I'm going to open the line LSTM CTC file. And so this is some network code. So right away, in the first few lines here, there's something that you'll see that's different than in the character predictor model that we trained. And the thing that's different is that in the character predictor, we have a single input, which is the image. But here, we've actually created a few inputs to the model. And the reason for that is, like, in order to compute the CTC loss, it needs to have access to the input image, but also the length of the input sequence. And then in order to compute the loss function, you also need the label and the length of the label. And the reason that we're providing the label and the length of the label here, as opposed to in the model, and like kind of breaking our abstraction, is because it's just easier to illustrate how you can compute the CTC loss and Keras by having them next to one another. But exercise for the reader would be taking all the stuff out of this network function that should not be in the network function. So taking the label length out and taking yTrue out. So yeah, I would recommend like exploring on your own how you might do that. All right, so another thing that's different from how we've created our networks before is that our LSTM function actually now has a conditional depending on whether we have a GPU on our machine or not. And the reason for that is there's this super efficient CUDNN LSTM implementation that works on a GPU and doesn't work when there's not a GPU. And so this is just kind of a flag to say, if we're training locally, then we just use the default LSTM class. But if we're training on a GPU, then we train with this more efficient CUDNN LSTM. All right. Yes?
Quick question. And is there any reason why you want the input length and the label length to be different? Is it for translation?
Yeah, so is there any reason why you'd want the input length and the label length to be different? Yeah, so it's a good question. So the label length is, in general, can vary quite a bit, right? So the label length is like the length of the sentence that you're producing. And so the way that this model works is it produces something that is a fixed length, and then it applies some rules to make it down into a shorter length. And so label length is telling you like what's the right shorter length to make it into. And then the input length is telling you what's the length of your overall like input image that you're feeding into the model. And so like in general, that won't really change, but it's present here in case you need it to. Yep.
How to determine that output labeling? What if the sender is actually longer than?
So the question is, how do you determine the output label?
Yeah, no, we fix the output labeling.
Yeah, so the output labels are just, like that's just determined by your data set. Yeah, so this is a great question. So the question is, why did we pick going in this order? So like first predicting a character, and then understanding a sentence, and then finding out where the sentences are in the entire page. So like one principle here that I think is super important is generally when I'm working on a new machine learning problem, like you want to really ramp up very gradually in terms of the complexity of the problem. And the reason for that is, and I'll talk a lot more about this tomorrow, but it's just so easy to have bugs in machine learning code that are very, very difficult to catch. And if you start with a very simple problem that you know should work, then if something doesn't work, then you know it has to be a bug. And so like the principle is start with the simplest version of the problem, and the simplest version of the problem in this case is predicting a single character. I think from there, the reason that we went to sentence instead of bounding box for the sentence is that it's just it's more similar. But I think also a reasonable approach would be to start with predicting bounding box of the sentence, and then later move on to character and then line. Okay. Yeah.
I would maybe also add, you can imagine a non-deep learning solution for finding lines, but it's kind of hard to find a non-deep learning solution to recognizing the actual text within a line. So I think it makes sense to address the harder problem first, and then worst case, you don't even use deep learning for finding lines.
Yeah, it's a great point. And I guess the last thing I would say on that is, in practice, so like we've made a jump here from, training Linnet on a single character to training this like ConvNet that's being passed into an LSTM with CTC loss on lines. That's a very, very big jump. And like if I were actually working on this project on my own, I would never make that big a jump. Like when I was happy with the character predictor, I might try a much simpler model first on the line data set. And we have an example in the code base of a simpler model that you could train that you should play around with on your own. Yes?
If you were in like a real environment, what would your time estimate be on like getting to this stage, starting with single character development?
Yeah, it's a really good question. So how long do I think it would take to get to this stage, starting with single character development? Well, I think that the single character development is a very simple task, and you can, basically should be able to do this with off-the-shelf ConvNet. And so I think it might take to purely solve that without creating any of the code base, the more sophisticated code base around it might take a day or a week. But then there's also, we're actually at a stage with this code base where it's relatively mature, and we can kind of easily add things, and we have tests and things like that. And that takes much longer. I mean, it's probably like a month's worth of effort. Yeah, question?
So we trained Linnet on the characters. We load those weights into the full LSTM model. So the first part is already done for us?
Yeah, so we train Linnet on character, and then the question is, do we load those weights into the LSTM model? No, we don't. It could be interesting to try pre-training, you use those as pre-trained weights. I don't think you'd want to just use those weights without further training them, because those weights all are trained on a data set where all the characters are in the center of the image. And here we have characters that are offset. Okay. I think, let's see, I'll finish going through this, this network code, and then next time we'll look at how we can train it. So the first thing that we need to do is, so remember that we have essentially a ConvNet that's passed over many patches of our original image. And so we need some way of telling the ConvNet which patch of image, all the patches of image that it needs to predict on. And so the way that we did that here is with this function called slide window. And what slide window does is it basically says, for a given window size and stride, so how much we move the window each time, I'm going to go to our original image and extract all of the possible windows from that image. So take the first if the image is 28 pixels tall and we want our window width to be 32 or 28, then it'll take the first 28 by 28 slice of the images, and then it'll extract those. And then it'll move over by our stride and extract the next 28 by 28 patch. And then the result of that, it's going to stack that all into this tensor that has some batch size and then some total number of windows, so the total number of times that we've done this 28 by 28 extraction. So this is like kind of an extra dimension on our tensor. So it's going to be a 5-dimensional tensor. We have the batch size, and then we have the number of windows, and then we have the image height and the window width, and then the number of channels is 1. So that's the operation that pulls out all of the 28 by 28 windows, or image height by window width windows that are present in the original image. And then what we do is we apply a Linnet. So again, really simple convolutional model to, so we're using the Keras functional API here. And so this call actually creates a function that we then have to apply to an input. And then we're going to create a model that takes, that maps the inputs of this convnet to the second to last layer. So we don't actually want to take the softmax. We want to extract the fully connected layer to use that as input to the LSTM. And then we apply that in a time-distributed way. So that means that we apply identical convnet at each time step. So at each step on the second dimension of the data after the batch size. And we pass the output of that to an LSTM. And then finally, the output of the LSTM goes into a dense layer. OK, and then the last thing that's happening here is we need to compute an input length for the sequence, because that's an input to the CTC loss. And we need to compute the output of the CTC, the CTC output from the model. So compress that longer sequence into a shorter sequence. And then effectively, we can just pass the we can just pass like kind of the inputs that we've created into these built-in functions in Keras that allow us to compute the CTC loss and the CTC decoding from this model. So we're taking advantage of some magic functions that have nice implementations of this like kind of complicated training method. Yeah.
So it looks like you're training both the CNN and RNN at the same time. Is that right?
Yeah. So this model is being trained end to end. So there's CNN being fed into an RNN being fed to the output, and then the loss from that output is backpropagated all the way through the network, including down to the CNN weights.
Would it make sense in some cases to split up, like training CNN on a single character recognition, where you had a separate data set for it? And then
Yeah, so the question is, would it ever make sense to train the CNN first on a single character representation? And I think the challenge there is, so you could do that. Like you could split up your data set into, you'd have to capture the diversity of, having some input, like some characters that are fully in the frame, some that are halfway in the frame. And so you could train that separately first and then pass that as the input. And that could be an interesting thing to try. But oftentimes, like training end-to-end works just as well. Yes?
There's some kind of transfer learning here, right? So you're using neural net, which actually predicts 10 digits. And you're taking the second last layer and feed it to LSTM, right? So
the question is there transfer learning here? The answer is no. You could do transfer learning here. Transfer learning is when you train first on one data set, and then you use the weights that you train on that data set as an initialization to train on another data set. We actually haven't told you anything here yet about what data set we're training on. And so it's very possible to use this model in a scheme where we're doing transfer learning, but that's not what we're doing here yet. Yeah, I'll take one more question, and then we should break for lunch. Yeah.
When you connect two models like you're doing here, how do you decide which layer of the first model you're going to use as input for the second?
Yeah. So the question is, if you're connecting two models, which layer should you connect? So you could connect the last layer, you could connect like the second layer, or any layer in between, right? And so the answer is there isn't really a hard and fast rule here, like many things in machine learning. But the thing that I usually see people do is to take, if you're looking at a convnet, for example, to take one of the earlier fully connected layers. So the idea is you want to take something where the model has had a chance to compute, to do a lot of computation to figure out the right features, but it hasn't actually converted those features into outputs yet, because the outputs might contain less information than the features, and you want to pass all the information to the next stage of the model. Okay, great. So next time, we'll talk about the data set that we're going to train this on, and we'll try training it, and then we'll talk about some of the tools that we use for training. The next thing that we're going to do is we're going to have our next sponsor, who's Baidu Ventures, come and just say a few words, and then we're going to break for lunch. And we'll see you, after that, we'll see you all back here at 1 o'clock.
Can I ask something before?
Yeah.
The weights and biases instance didn't spawn for me. Is that because we don't have enough nodes?
Yeah, we've been having trouble with the cluster that we're supposed to spawn nodes on, and we're going to be working on that over lunch, and we'll hopefully it'll all be working later this afternoon.
All right, thanks.
Mm-hmm.
Yeah, join syshelp. If you're not in syshelp, then ping me. All right.
Okay, great. Thanks, everyone.
Hey, so we are at a 2-day conference from 8 a.m. to 8 p.m. I'm a reasonable person. I don't want to be the only thing I'm the only thing that's standing between you and lunch right now, so I'll keep it very brief. My name is Fang. I work at Baidu Ventures. We are a $200 million fund, and we're a non-strategic investment for Baidu, which basically means that they give us money and we do what we want with it in order to get financial returns, which is kind of good for us. The only thing we focus on is early stage AI and robotic startups, typically ones that are enterprise facing. And actually, PRBO startup Covariance, we're an investor in that, and it's been like a really great working relationship with them over the last year. So we can, go out and chat with him about the sort of value add we have given him as investors and a really good working relationship. What I should mention, I suppose, is that there's 4 of us in San Francisco, and we cover all topic areas of AI applications, such as startups, we're industry, sector agnostic, so anything from agriculture to transportation to retail. We also look into a lot of frontier tech, so it could also be LiDAR companies, different types of radar companies, sensor companies as well, and also synthetic biology, computational biology. So for anything along these lines, feel free to get in touch. I'm from New York City. I'm very direct and honest with my feedback. So if you want to bounce ideas, I'm more than happy to do that and give you honest thoughts about what works and what I think doesn't work. And I'm pretty opinionated on my thoughts, but I try to back it up with experience. Anything else? Just come up. I'm pretty friendly. Yeah. Thank you guys for going through this over your weekends, and see you guys for actually making this happen.